quick introduction to our speaker today, Pejman Ghorbanzade, and that's his Twitter handle. He's the founder and CEO of Tuka.io. He's previously a senior software engineer at Canon Medical Informatics and VMware Carbon Black. He's interested in problems related to software design and maintenance at scale and over time. He's also very passionate about solutions to improve stability and maintainability of software products. So with that, I will hand the stage over to you, Pejman. I'll stop sharing.
Thank you so much. That was a great introduction. I appreciate that.
You're welcome.
So hi, everyone. I'm Pejman. I want to first thank you for being here. I know that it's, past your work day, so you must be, exhausted already. The fact that you're here means a lot. I hope that this would be useful to everyone. And I can't wait to share what I've been preparing for. So I assume you see my screen right now. The title of this talk is Continuous Regression Testing in Java. Just a little bit about myself is that I currently live in Minnesota for 6 years. And I'm presenting from an empty room because we are moving to California at the end of this month. So it's a little fun fact here. I want this talk to be interactive so that I don't bore you to death. So if you have any questions, please feel free to send in the chat. I'm going to try my best to have an eye on the chat. And even if you have just some comments that you want to write, please feel free to write that. So don't feel like you need to ask for permission to jump in. The idea here is that we all take away something useful from our time. So the talk that I've prepared, I think it has you could say that it has 4 parts. I just want to basically briefly say what continuous regression testing is. And then, how, what I'm going to give you basically a demo just to show you a few methods and tools that exist in the Java ecosystem for using regression testing for testing real world software. And then if we have time, then I'm going to actually show you how to do continuous regression testing instead of just regression testing. But since you're going to hear the word regression testing a lot, I want to pause here and say if you have, maybe this is actually a good practice too. So you could write in the chat whether you have heard of regression testing or are using some kind of regression testing in your day-to-day software workflow. So yeah, I'm waiting for someone to say, okay, yeah, I see a lot of yes. Cool. So let me ask a second and last question. Have you, do you think you need some explanation, a thorough explanation of what regression testing is? Is there anyone who has not heard of regression testing? Okay, great. So so many yeses. I still haven't seen. Oh yeah, okay. So I'm going to explain. Of course, I'm going to explain regression testing, but I'm going to make sure that everyone is on board with what we define as regression testing. So all right, with that, I think Mary did a perfect job of introducing me, so I'm just going to skip this slide. Just wanted to say that before building Tuka, until last year, I was working for Canon Medical Informatics for 4 years, which was a phenomenal company. I had a lot of fun working there. The picture you see on the right side is basically an output of the product that we had built, which was for 3D visualization of MRI and CT scan data sets. So we were building medical software, and the idea behind all of this, kind of my obsession with regression testing is in some ways kind of related to my experience working there, since we were building medical software that required exhaustive testing, and we had plenty of infrastructure in place to make sure that when we are writing code, we can find and fix our bugs as soon as possible. So just some fact here. But before we jump into regression testing, I want to take a step back just a second and kind of reflect on what we all consider as software engineering. I think I had this discussion actually yesterday with a few friends about what are the differences between programmers and software engineers. And I know we usually have these discussions every once in a while, and it's more like kind of a board game in many occasions. But at the same time, I feel it's good to somehow remind ourselves what we think software engineering is. This is completely subjective. I am only sharing my own understanding and kind of personal opinion on this. But I think I regard programming as basically the craft of writing, using the computer to solve a problem. So that problem oftentimes, especially for like, early entry-level engineers, is an abstract problem. The way that we learn programming in schools is, here is this algorithm that does X, and that X more or less looks like a puzzle. So in a lot of cases, I kind of associate programming with solving, writing programs that do something with the computer, and it's the difference, the contrast with software engineering is that it's not just about writing the program, it's about building software. And again, it's more or less just a choice of words, but when I think of building, the difference here is that it also involves kind of maintaining the code that you write. I think there's this quote that I really like from Titus Winters that says, software engineering is computer programming integrated over time. You write a software to basically solve a business problem, a real world problem. And real world is messy. So there are all these kind of stuff that are not necessarily related to the computers anymore. It's more about the real world. Like, our software worked just fine until yesterday. Now, some user is asking for some feature that we don't have, so we should add it to that kind of that our solution. Now we add that, but now we have a more complex software. How do we reduce the complexity? Then we make changes. How do we make sure that that customer is happy? And all of everything that kind of you already know. This picture that I have added in the right side is a building called India Bell in Indiana. That was actually a telephone switching kind of building. So it had it was considered a critical kind of infrastructure building for the city, but at the same time, in 30s, I guess, they wanted to run a highway in the middle of the city, and therefore this building was kind of in the way. So they had two choices: whether to completely destroy this building, or to just make way for that highway somehow, that they could still make this building work. Building exist. So, and what they did, stunningly, was that they decided to kind of rotate the building 90 degrees so that they could pass the highway. But one of the, kind of, again, a testimony of how real world is messy and, what business values are, is that this was an important infrastructure building, so it had to be functional all the time. So a requirement was they had to do this kind of rotation while everybody woke up to go do work in that building. This project kind of shows that it's not just about, learning how to build some building somewhere. It's, kind of taking care of it and making sure that it adds business value and generates a value over time. So kind of a long intro, but I guess what I wanted you to take away is that kind of a strong emphasis on the business value. And I think one thing we quickly learned when we are working somewhere as a software engineer is, if you want to build a business value, it's very important that you have a good understanding of the solution that already exists, the code base that you're working on. If the code base is full of technical debt, of course, there's higher chance that the little feature that you want to add would take more time, or maybe it would add risk just to add it. So in a lot of ways, compared to like civil engineering, if they both have that kind of building concept, the difference here is that software engineering is kind of like building with mud, because the medium that we are working with, it's so tractable, it's so abstract that it can easily bend one way or another. So to make sure that we can build software and add more and more to the existing solution, means that we need to make sure that the existing software works correctly. That's where testing comes in. Testing is essentially making sure that so far the work that we've done to solve the business problem that we want is safe. So then the question becomes, what are good tests? What would you consider a kind of a test with high business value, with high return on investment? And I think, again, all of these are very subjective, but I categorize good tests as tests that have 4 kind of characteristics. One is that they should be cheap to write. It shouldn't take you long to just basically make the test work and test something. Of course, they should also be easy to read, because they're going to be around as long as your code is. So if you make this kind of test framework that is so abstract and so complicated that no one else in your team is able to make sense of it, then of course they're going to write their own kind of abstract and complex test infrastructure, and it's all going to just basically reduce the business value and the return on investment of those tests. The third kind of characteristic is that they need to be fast to run. And we're going to get back to this a lot, but the reason for this is that if it takes you a long time to get to that kind of value, the feedback the tests provide, then of course, the time that you are waiting is the time wasted that you could do other things that are important to your business. So therefore, that feedback cycle, as short as it can be, would basically add more value to your tests. And last thing is, your software is always changing. Therefore, it's important that you could change your test too. Now, if every time that you want to go and update your test, you need a long time to just understand what the tests do and how they work, then of course it's going to be difficult. One thing that is very common frustration for me as I reflect on my experience as a software engineer is, we always have these unit tests all over that we want to have because they add code coverage for us. But then at the same time, those unit tests, they are kind of very susceptible to changes in the software. So every time we make changes, we have to go make changes and updates to all these unit tests that we have. And it's always, it feels too mechanical to, feel valuable. So therefore, good tests, in my opinion, are tests that kind of give you that value without the extra effort that you feel they involve. Of course, to get to that fast to run kind of characteristic, to make sure that our tests are fast to run, the general consensus among developers and software engineers has been to favor writing unit tests that could be, that are so small in terms of scope that could be run faster. They don't have dependencies on external systems, so therefore they take, kind of faster to run. Now the picture on the right is kind of that same test pyramid that I assume we are all familiar with, that says the more unit tests that you have, the more kind of Oh, and someone in the chat asked, please define fast. I'm in fast in terms of runtime, the time that it takes for us to run the test and get the value. And that value is essentially whether our code works correctly or as well as before. That is what I call the time to like the feedback cycle. Now, how fast is again very subjective. Depends on the software that we are building. Sometimes, the software is so complicated that we have release cycles that span over a month. So in that case, maybe because the nature of the software is so mission critical, and yeah. So maybe. Okay, I'm getting distracted by the chat, but the nature of the software has to be kind of mission critical. So therefore, engineers are happy to spend more time making sure that their software is working correctly by having kind of deeper testing that would take longer time because they want to test the way that their software behaves out in the world. Now, how fast is really fast for, say, unit tests? Again, that depends. But in general, a unit test shouldn't take more than at least a few tens of milliseconds, at most a few tens of milliseconds. Because in that case, like if you have a lot of unit tests, you want to be able to run them as part of your CI for every commit that you are making, for every little code change that you are making. I would always think of it this way: if you kind of go one level of abstraction higher than just what tests do we have and what do we call them? Maybe they are unit tests or integration tests. The important thing to take away from those tests is whether our code works correctly. How fast can you get to that is important. It's more important than how fast an individual test is running. In my experience, if it takes more than a couple minutes for me as a software engineer to understand whether this code change that I'm about to submit a pull request for is working correctly or not, then my tests are probably slow. That they need to be faster. Someone else might be happy spending some time. They might in fact say, it gives me enough time to go grab a coffee. Again, it's subjective, but at the same time, for real world software, getting to just a few minutes until you get that confidence means that your tests need to be really fast in terms of individual test runtime for every test. They should be only a couple of milliseconds. Again, if you're talking about higher level testing, like integration tests that deal with services that we have for our software, then of course they take longer time. I really love it that we have this conversation in the chat. Thank you so much, Michael and everyone else. So the question here is how often you have to run the test might factor in as well. Oh, it's not a question. Oh, sure. Yes, I agree with that too. Okay, so if you don't mind, I'm going to, again, please keep these kind of comments coming. I love it, but just for the sake of time and because we have hands-on demos too, I'm just going to move ahead one slide. So again, we have these tests, and if you have good practices in our team, as software engineers, we say, here's our day-to-day workflow. We go in, we write some code, we test them, we create a pull request for them, we review the pull request, the change request of our friends and colleagues, and we kind of decide that, hey, this is actually a code change that we want, so we make commits and we merge pull requests. In a way, software engineers, the vocabulary that we use kind of revolves around reading the code, writing the code, reviewing the code, testing the code. But there's also this other kind of loop in the world of a software engineer, which I think sits out in the outer layer. It's all about the business. It's no longer about the code. It revolves around the business. From the business standpoint and perspective, we want this code to do something meaningful, which means we need to ship it to the hands of our customers, then make sure that it does what they want. So it's all about planning some feature based on our understanding of the market and the feedback from our customers. Then, of course, those features need to be implemented. So here's the implementation. Then we need to make sure that those implementations are working correctly. So we do this kind of round of testing for those changes. Then we deploy those changes to the hands of our customers. But our work is not done there. We need to make sure that those changes work correctly. So therefore, we have all these observability kind of tools and methods to make sure that the code that we have deployed is working correctly. And then, of course, then it's not complete if you don't get that feedback from the customer, whether we solve their problem or not, whether we solve that kind of need that they were looking for. Maybe it was a feature that they requested. So it also has that kind of aspect of let's kind of iterate over the business value of that feature. So that outer loop usually takes longer than just basically adding a feature. And I think that's not necessarily an issue by itself, but there are potential issues here where the two loops that we usually deal with are kind of out of sync. Now, they don't need to be kind of one iteration equates another, but at the same time, there are a lot of times where software engineers feel like, all right, I made my code changes, but now I have to wait for this QA team of my business to make sure that those changes are right. So the testing is done by someone else. And that feels, kind of an interruption to this kind of workflow, the smooth, running of these two loops together. There are other cases too, where like we have made all these changes, but we are kind of blind because we haven't deployed them yet. And then we deploy them, but then the marketing side and the business side of things are kind of, they are not paying as much attention as to the changes to our software as it deserves. So usually, like there's this engineering team and then the other business side of things that have conflicts. At least without naming names, I've had experience where we kind of blame other departments, but for saying, well, our software is getting old because we don't know what is out there and we don't do a good job of, getting that feedback from customers. So, but if you think of great teams, I think what the common pattern that we see is that there is this tight loop between, the time that you add a feature and the time that you get you iterate over that. You iterate over your entire product in a way. And that those kind of businesses, they tend to be product focused. So therefore, engineers take the center stage. And that's why actually engineers are more productive in those companies, because those two loops are kind of very, very well synced. All right, so I guess my point here is that it really matters when we kind of get that feedback from the world that our software is working correctly, and that we should go ahead and make further changes to it. You might have seen this kind of table in a lot of places, of course, but the idea here is that depending on how long that feedback cycle is, the cost associated with defects in our code would basically increase. In cases where we have to rely on our customers to file a report to us to say, oh, we have this bug and defect, well, that's a long feedback cycle, and therefore it's going to be very costly to our business because there are all these customers that are not happy. And once they file an issue, it would take a long time for some software engineer to pick up the task, go make changes and deploy again. So the fast kind of iteration really matters. And if we, think of it from the cost perspective, the faster we could iterate over our product, of course, there is less cost associated with every kind of bug or anything that needs changing. So The best case scenario is that you get to magically learn all the issues with your code and make sure that your code is working correctly, just as you're writing it, which is finding bugs during the development stage. That's why there has been historically this kind of emphasis on writing unit tests, because unit tests are the tests that historically are run by developers. And I say historically here because that doesn't have to be the case. These days, again, technology has improved so much that, in fact, running higher level tests, right, integration tests and end-to-end tests, don't take as much time as they took before. From the historical standpoint, we said, well, end-to-end tests are bad because they're manual. It takes time for someone to do something, so therefore, we should have less of them. But if they are automated and they take faster to run, then of course, there doesn't need to be that kind of a stress to writing unit tests as much as it used to, be 10 years ago. And we've come a long way. I assume you've seen integration test kind of solutions out there that do service kind of integration testing. And they are meant for use by developers. Again, at the end of the day, it's this engineering team and engineering department that do those tests, usually automatically. Now, I say, the good parts, but the bad part is still, our software industry is struggling with this kind of feedback cycle. It still takes 23 days for an average software engineer in our day and age to get the confidence that, hey, this change that we made just now is working correctly. And 23 days is a long time. By that time, the software engineer who wrote the code has probably forgotten the context. They have moved on to some other task, and therefore, if they find out that, hey, there was something wrong, it takes a long time for them to get back in the zone to understand how the software was working. So I'm going to take a pause here and read the chat here. They say that Bob Martin had an idea to charge developers for any serious prod bugs in clean code. Yeah, so actually, yes, that's true. But at the same time, it's kind of, it's not the norm. I'm sure you would agree that the norm here is that we blame each other, but we don't necessarily, kind of solve that problem. We all know that it costs us a long time for basically for us to get some feedback, but we kind of complain and rant here and there. But usually it takes us, a really serious bug to say, all right, we need to revisit our practices and processes. So I would say it was great if we could all, as much as we have stand-up meetings and, kind of weekly meetings, we have maybe monthly brainstorming discussions about our processes and how we could improve them. But and some companies, they do that. The companies who are actually more concerned about the productivity of individual developers, they also are, they get more value out of those developers. So therefore, they get more business value for the entire business. There's this kind of, I would say, cost associated to our processes. And as software has evolved and changed over time, it's great that we kind of not take for granted all these practices, like for the testing permit that I showed you as much. So in the interest of time, I want to now kind of shift focus on regression testing. I think we all had this discussion about the feedback cycle. I wanted you to get this kind of this in the back of your mind as we talk about regression testing. It's all about getting to the feedback for software engineers, and what tools and products we could use to enable that kind of feedback cycle automatically, or in a way that does not require basically asking a QA test person to do use and kind of a software that is meant for QA. So I'm going to tell a very short story of how I came about, the regression testing. I gave you a hint earlier, but at Canon, we had this kind of project of refactoring a very kind of important, critical data ingestion pipeline that we had. It was written over many years. It was generating money for us. It was very critical to our software. But at the same time, the original authors had left the company. The code was kind of, it didn't have good tests. So therefore, it had been left in this state of legacy code for so long that no one was kind of there to approach it. We had this kind of issues where we, had a bug report from our customers, but we said, well, it takes so long for us to fix this, issue, just for us to understand where the root cause is and what the fix should be, that we said it probably isn't worth the business value. And that's really bad if you have a critical component of your software that you cannot change, then of course you're missing value there. So for us, this pipeline was 500,000 lines of code, and it was very clear that we could no longer just maintain it. We had to replace it with something. Maybe take a few components out of that, kind of subcomponents out of that large component. But again, we had to rewrite or rethink the entire pipeline. But building a medical software, there has this kind of side effect that you are always kind of concerned whether you are breaking something. So it was very important for us to do this kind of replacement that would take obviously a long time because of the large size of the code, in a way that the code that we are kind of deploying is still functional, that our customers could still use it. And the first kind of approach solution we had in place was very naive and simple. And I've heard of this from many software engineers that they use this kind of approach too. So it's not I'm not going to be very critical about it, but the idea here is that you have this legacy component, let's say system A, and this new component that you are writing, system B. How do you make sure that system B works the same as system A? Well, of course, you could write a test that would call system A for any given input, and then call system B for any given input, and then it would just compare the two outputs together. And every time you make changes to system B, because you are making refactors and adding features to get to feature parity with system A, you would have to rerun this whole test. So the reason I feel is suboptimal is that every time that we are running the test, we need to invoke system A, which was the legacy system. But system A isn't changing. It's the same code as it's been for so long. So therefore, the time that it takes for us to run that old system is the time that we are wasting in our test. Again, think of the feedback cycle. Another thing is that the test process is calling system A and system B at the same time. So the dependencies and the system environments should be kind of there in our testing infrastructure for the two systems, which make the entire test process very clunky. Plus, that test, because it's very kind of geared towards testing the two systems, it's very specific to those systems. So any kind of infrastructure or code that you're writing for the test itself cannot be reused for some other project someday. So the cost associated with this test is, I would say, very high. The alternative to this is what in the larger software engineering world, kind of known as a snapshot testing. It's the fact that, hey, because system A isn't changing, let's just take a snapshot of its behavior and performance potentially for a given kind of for the given set of inputs. So whatever input that we want to test our software with, every time that we come up with a test case that is important for us, we would run it through system A, the legacy system, and it would generate that kind of a snapshot. It's a kind of a description of how this test case behaved, how this input behaved. Usually, that snapshot is just the output of the system. it would say, here's the textual output, or here's this image that the pipeline spit out. But then the advantage to having those snapshots is that we could just store them somewhere and not have to run the legacy system A every time. And therefore, we are saving us a little time. Obviously, to make use of that, those snapshots, we need to generate a new set of snapshot files for any given version of our code. So in this case, system B, as we are working on it, would basically, during the test, generate similar snapshot files that we could take and then go compare against the snapshots generated for the legacy system. Essentially, by just diffing the two set of files, we would say, all right, our code is working as well as before. Note that in this case, we are not testing for correctness. We are just testing whether our system worked as well as before. Maybe whether it has the same bugs as before. But the problem with this approach is that dealing with files is not very fun, especially for real-world software where you just don't want to test your workflow with 1 or 2 test cases. You have hundreds and thousands of test cases that you want to feed into your system. And therefore, for every test case, if you have to generate a file, then you have hundreds and thousands of files to compare against other hundreds and thousands of files. Let's just say that there are differences. Then it's possible that a subset of all these files now have differences. How do you make sense of those differences in data scale? How do you say, oh, because we changed this variable and now the textual output of our software is kind of indented a little bit. Now our software is working the same. This constant monitoring of those files and kind of storing that kind of representation of what the correct behavior is, that is very frustrating at a scale for a real-world software. At the same time, this concept of snapshot testing is very, very common. Not every company is using it, but at the same time, it solves a kind of problem and a use case that unit testing might not necessarily be effective in solving. So I know that I talked a lot. So before doing a more hands-on demo, let me ask, do you have any questions or any comments in the chat? I don't see any new comments or questions in the chat. So maybe you don't have any. Maybe this is boring. I don't know. So I'd love it for you to give at least some kind of feedback. If you want me to go faster or slower, just let me know. All right, so let me show you the snapshot testing with a few examples. First of all, the term snapshot testing was actually introduced originally in the Jest framework that is more or less used for the JavaScript ecosystem. But at the same time, there has been this practice even before Jest. We called some called it golden master testing. Some called it just regression testing. The idea behind this is you just basically create a bunch of files. I have a few tools that are relevant to the Java ecosystem that I want to show you, but in the interest of time, I'm just going to use one of them, the one that is kind of more popular, and then leave the rest just for you. And here is basically the oldest kind of snapshot testing framework that I found on GitHub just by searching for snapshot testing. And you see here that the last commit was 2020, so it's been a while. And it's not very popular, but at the same time, it solves that need. It behaves just like any snapshot testing solution. The idea for it is that basically you create, it works just like a plugin for your JUnit platform. You create this you use this library to create files off of a string that is representing your description of your behavior of your software. And then the test essentially is kind of checking whether the two files are identical or not. and it uses kind of resource path to find what directory it should generate the baseline files into and all that. The main theme in a snapshot testing is you need some place to store your snapshot files, the ones that you trust, the ones for that kind of system A that maybe you ship to your customers, or you did a great job of testing so that it behaves as you want. And usually snapshot testing tools, they use the version control system. They just have a directory where they check in all these files. And I'm going to get to why I think that is not a great thing to do. But at the same time, that's like why this library is using resource path for those snapshot files. Then the next library that is available is JSON snapshot. And this I liked because it basically tries to replicate and imitate the behavior of Jest, which nowadays, if you've built code with JavaScript, you probably have used Jest. So therefore, it's a very common pattern. So it uses the same kind of syntax and patterns that the Jest snapshot testing framework is providing. Specifically, it just basically says, if you have a string and you want to check it against your snapshot file, you would basically say, expect my variable to match the snapshot. And that's it. So essentially, it's kind of like an assertion without the expected value. The expected value in this case is replaced with to match the snapshot, whatever is in that file. And of course, if the file doesn't exist, then of course, there's nothing to compare against. So therefore, the test would fail. And that's very common for any kind of a snapshot testing library. The third tool that that is kind of more popular and maintained more than the rest is Java snapshot testing by Origin Energy. And it's essentially very similar, so I'm not going to repeat myself here, but what I really like about these tools, the snapshot testing tools, is that they all fit very well with this kind of platform and test practice of, hey, we use Gradle tests to run all our tests. So they kind of say, all right, there is this existing pattern with JUnit, for instance. Let's just kind of use that same pattern, integrate with JUnit so that just like you have any kind of test, any unit test, you would create a function, you add an annotation that this is a snapshot, and therefore it just works as a snapshot test. So I think that this library, the reason why it's popular is it provides a better developer experience for doing regression testing. Snapshot testing. But the one that we are going to use today is called approval testing. And I used this one. I picked this one because there are implementations for almost every language, every popular language. So therefore, it's very easy if you are used to certain concepts of approval testing to say, all right, if I'm building software in some other language, I'm just going to use the kind of similar library, approval test library. So the one, of course, that I picked for this demo is approval test for Java. And in the chat, there's a question, what is approval testing? It's exactly the same as snapshot testing. It's just another word. It's kind of coined by the authors of this library. So it's not some different practice. It's yet another snapshot testing with a different name, of course. The idea is exactly the same as you are going to see. So before just showing you links on GitHub, let me just show you the code. For this code that I'm going to show, I don't know if you have used coding katas before. These are like example kind of projects that are really suitable for practicing refactoring, for instance, or testing, especially if you are doing mob programming or pair programming, and you want to kind of educate everyone on your team about a certain kind of practice that you want everyone to do, doing a code kata could actually be a valuable use of your team's time. Now, coding kata could be anything, and there's this kind of repo, awesome katas that have a pretty good list of coding katas that you could do. The one that I'm going to use for this demo is the very first example here, the supermarket pricing. Specifically, the code that I am going to show you is this repo, supermarket refactoring kata. It's essentially like basically it has implementations of the supermarket example for different languages. And the language, of course, we are going to work with is Java here. The idea behind this supermarket example is, let's just say you are building a cashier kind of software, the checkout system for a supermarket where you have carts. So your users go add stuff to their shopping carts, and then they want to check out. So in this case, you can see, how this software works by just reading the unit test for it. It creates, let's just say we have a toothbrush. That toothbrush has a certain price. Then we have a bunch of apples in kilo as unit. And then we add some apples to our catalog. We create basically this cart, and then we add our stuff to cart. And then the cashier system may be running some special offers for certain items, maybe a buy one, get one, something like that. And therefore, like once you have a shopping cart, you could just basically run it through the cashier system and see if, at the end of the day, the receipt that the cashier is generating is kind of matching your expectation. In this case, the receipt is the final product of our software. We are just basically generating a receipt for every shopping cart. The receipt now could be complex. You might be checking out multiple items that have different kind of offers on them. But at the end of the day, we all know how to test the software. If you were to use unit testing, you would say, all right, I have this receipt, having multiple methods to it. So let me just call this method and see if it matches my expectation. So I don't want to do kind of a refresh on our unit testing, but the core principle of unit testing is you have basically a hard-coded test case for every unit test that you are writing. You're saying, here's my shopping cart. So you have this kind of these products that you are adding to your shopping cart as hard-coded. And then once you create a receipt for that specific input, then you are going to compare them against something, in this case, your expected values. And those expected values are usually hard-coded. Because your inputs are hard-coded, they need to be too. So therefore, you have all these like basically values that you treat as expected values in your test code. That's not necessarily bad. Of course, we all agree that unit tests are very effective in testing certain things. But that means if you now make changes to the behavior, you might want to, you might need to go and update these expected values. Or maybe you add a functionality. Now you need to write a new unit test with a different set of test cases. So we all know how unit testing works. So I'm going to just remove this code and show you what if we wanted to use approval testing instead of unit testing. In this case, I have a receipt. So I'm going to use a receipt printer. Now, this receipt printer might be coming with the code under test, or it might just be some class that we've created as our test code. It doesn't really matter. The idea here is that I have a receipt printer kind of created. Now, in this case, the repo that I am using, it has this kind of pattern of you create a receipt printer first, and then you have this receipt printer that has a print receipt method. And then that method takes a receipt, and it basically generates a string for you. Now, it generates a string, but that's the output of my test. So therefore, I could use approval testing to treat that receipt, the string representation of the receipt, as a snapshot of the test. So in this case, I would use approvals dot verify, and then the input to this verify method is the textual representation of my code under test. So here it's like basically we're saying every time we have this kind of shopping cart as our test case, we are going to create a string that we then are going to store in a file. Now, of course, the first time that you run this this test is going to fail because you're essentially just writing a file. You don't know what the expected output should be. So I'm going to just run Gradle test here. And as I said, the test has failed. I see that the test has failed because of basically a failed approval test. And the output says that it was expecting a file here called approved, but there was no file, so therefore it failed. Now, if I check my tree here, I see that this running of the test has created this file in my source code. In this case, right adjacent to my test code, which is basically supermarket test, the name of my overarching kind of test function, and then dot received. The received means the file, the snapshot that was generated for the actual version of my code, the same code under test that I have right now. And the test failed because there is no corresponding approved version. So if you look at the received version, here's the receipt for that small kind of example, the test code we had. The receipt is basically saying, hey, I have 2 pounds of 2.5 pounds of apples. Every pound is $1.99. Here is the total. So instead of writing assertions for every detail of my receipt, now I just basically have created my receipt and I'm storing it as an approved file. In this case, how I'm doing it is I'm just basically renaming this file as approved. The renaming is a step that a software engineer is taking. It's a manual step. And it's an important one. You are approving the actual behavior of your code. And that's why the authors and maintainers of this library decided why this practice deserves to be called approval testing than a snapshot testing. It's the emphasis on the notion of approving an actual behavior. So by creating this approved test here, now if I rerun the test, and by the way, I didn't make any change to my code under test. I just changed the snapshot test file. Now you see that the test has passed. The reason is that this time, when the call to the call here to approvals.verify runs, it essentially checks for that approved file. It finds it. It compares the actual textual representation of my receipt against the content of that file, and it sees that it's identical. So it passes the test. The problem kind of happens when the actual the new version of my code generates an output that doesn't match that approved file. So in that case, all the snapshot testing frameworks, they just say, all right, we don't know what's what. It's up to the developers to go kind of diff the two files, the received file and the approved file, and just make sense of them. Usually, in larger teams, they write scripts usually in Python that would say, all right, we just want to diff a certain set of files and make sense of the output. But writing those scripts are hacky because, again, they're specific to they have assumptions on the content of the snapshot files. They're very kind of very much tailored for the test that you have written a snapshot testing for. So you cannot reuse them day to day for different workflows that you have. Another issue that is very common and kind of frustration with approval testing and snapshot testing in general is that, let's just say that our requirements change, and now we decide that in our receipt kind of class, we want to indent the entire file by a few spaces. In those cases, the output has changed. Now every line in our file has some spaces. How do you kind of verify that the differences that now have appeared when you are running your test are all kind of, they have the same root cause as the indentation and not something else because of your code changes? In a way, that kind of inspection of the test results of the two files, that is very mechanical and very kind of prone to risk in that you have a bunch of files and now you have to inspect every one of them individually. And again, another frustration is that you need to store these files somewhere, and when you are storing it to version control, I would argue that you are essentially abusing the version control, what version control is designed for, which is storing your source code, not your test results. In a way, snapshot files are test output files. So therefore, I would argue that having all these snapshot files stored somewhere and then constantly updating them every time a change happens is kind of more noisy than updating individual expected values in your unit test. So again, taking a step back, it's all about the feedback cycle and the simplicity of dealing with your test. Dealing might be reading the code. In this case, I would argue having 200 assertions in unit testing is very kind of very difficult. But having a simple line that says approvals.verify is kind of helping us not to have to spend our time maintaining all that code. But again, you want to argue in certain cases, dealing with the snapshot testing could be time consuming by itself because now you have all these files to inspect. Okay, so very good point and big, no for me. Okay, yes. Again, it's very, I'm not trying to sell you any kind of method for full transparency here. At Tuka, we are a very small startup. We don't have too much budget in terms of using all the best practices in software engineering. So we're just basically kind of sufficing to writing unit tests for certain kind of critical components of our software. So yeah, sometimes not every tool has to be used for a certain kind of business component. Now, all right, that was my demo for approval testing. Again, if you have any questions, please write in the chat. And I understand that it's 8:17, so I'm just going to promise that there are only a few minutes left to my talk. I'm going to give you another demo, but since it's Tuka, the product that we are building, I don't want to come across as salesy, so I've kind of shortened that whole process to just a few minutes. So now the third solution, the solution that I came up with when I was, when I had to my team had to deal with that kind of problem, a business problem that I mentioned, was, hey, how do we get rid of all these files, the snapshot files? How do we make sure that, if you have a variable somewhere that is not necessarily, showing itself in the output of our, kind of end stage workflow, that end output of our API, we could still kind of track it for regressions. Assume that, system of, 500,000 lines of code. Of course, it has multiple stages how do we add hooks to different stages so that if something goes wrong, we could say, oh, it went wrong in this stage, so therefore the root cause has to be in this component and this piece of code. In those cases, dealing with the snapshot testing has this kind of issue of you're kind of bound to the API that you are exposing. You can't just say, hey, this variable or the runtime of this function is very important to me, so let me just create a file for it. Because again, you're using the test code to describe what you want to capture as snapshot. That is by itself a limitation. So the idea for this kind of separate solution is that we have this new system that we have. So let's just basically run it with as many test cases as we have. But then instead of capturing the output, we leave it to software engineers to say what variables they want. In a lot of times, those values would essentially be the output of the test. But if the workflow is so complicated, they could say, I want every output of every stage of this multi-stage workflow, and that should work. Essentially, by creating creating a copy of the values of certain variables, then at the end of the workflow, we end up with this kind of copy of multiple variables that better represent the behavior and performance of our workflow. So therefore, instead of writing them to disk, maybe we could just say, here's the value for this variable, so let's store it somewhere in a database, somewhere else other than the version control. By kind of submitting all those test results to a third-party system or kind of third-party, I wouldn't say third-party, kind of an external system that might be running somewhere in your team infrastructure, then you're essentially eliminating the need for creating a snapshot files. And there is one advantage to using a separate system in that system usually has a computing resource. So therefore, it could compare those test results as they're being submitted. Because it now retains all the test results for different versions, that system could not only do the comparison of your test results, but also generate reports for you to visualize and look at. So essentially, the kind of core demo that I want to give you is a very simple kind of find a student example. But because I gave you this kind of description about the supermarket, let me just show you the code for the supermarket example. Let's just say it's the exact same code, that's 10% discount supermarket. We have some apples that you are checking out. Now with this kind of system that I mentioned, the one that kind of captures the value of variables, we could say, instead of using approvals that verify and passing the entire receipt, we would say, we can pass anything. We could track any kind of variable. In this case, I'm saying I want to track the total price of my receipt separately. As there's a method for it, so I'm going to call it, and I'm going to say whatever value that this is going to spit out for different test cases, it's going to be called, associated with this name, total price of my receipt. Then maybe we want to have another kind of variable that has discounts, and we want to track those separately. So we could check the, kind of the discounts that our receipt is having. The idea here is now if we decide to add a few indentation to the textual representation of our receipt, we don't have to change our code. The description is it only kind of includes what is important to us. Now that might be runtime of a few functions or values of a few variables, but because we're kind of surgically picking and choosing the variables that we want to track for regression, then it's easier to manage this workflow. And so therefore, as you see, maybe I have a few items on my receipt and I want to track them separately. So I can do that here and add every item to kind of a list. I can even write a serialization for the receipt item. For every item in the list, I would say, I want to kind of create this, to serialize this into an object. that is easier for me to compare. So in this case, the important characteristic of any object could be serialized as a member of what is at the end of the day would be shown as a JSON in that kind of third-party system. And therefore, you basically replace that one line approval verify with a few lines that would say, here are the important variables that you are checking. And then the system would essentially compare these data points individually. And if there are any differences, it would visualize those differences for you. The certain features that were missing and frustrating for me when I was dealing with the snapshot testing frameworks, I tried to solve them by creating this kind of system. Now, the demo that I want to show you, and again, I promise this is very quick, is that let's just say if you have a database for students, we have this kind of student profile system where a student goes, they add the usernames, and then we kind of fetch the basic profile information of the student, which in this case is the username, full name, date of birth, and GPA. These have different types, by the way. So one important, kind of requirement, if you want to, do regression testing for real-world software, is that we don't want to stringify anything. We don't want to serialize them in ways that would remove the precision in our comparison. So my kind of approach is, let's just basically compare these variables in the binary representation. We might, create a kind of a textual visual output when visualizing the differences. But if you have one variable that is double, then it's numerical kind of digits of precision is very important for us. So much that maybe kind of serializing it into a text file might just break the deal. So the idea, as I showed you, is that you essentially create a workflow, and you say, here is for any given test, here's what is my code under test. In this case, I am taking a username and I am passing that username to my find student function. And then that find student is giving me the student object, the output of my code under test. Now I can say, all right, the full name and date of birth and GPA are important for me. So track them to check them for regression. By doing this, first of all, we remove the need for explicitly hard coding our inputs, which is really useful if you have hundreds of inputs. So therefore, instead of repeating the same code under test and the workflow under test for every single input, we just have one single workflow. The way that we want to test our software is very well documented in this case. And at the end of the day, it matches our kind of mental understanding of what we want to do when we are writing a test, which is, I just want to call my test workflow with these inputs. So the input is always given as a parameter to your workflow. And then with that parameter, you can go to town, maybe, fetch something from a database and then use that as an input, or maybe go read a bunch of files and pass it to your work code under test. But at the end of the day, those test cases, in this case, the username is serving as the test case identifier. And that's basically how the system, the third candidate solution works, which I would say is more in line with regression testing as we know it, which is checking whether we have made changes to our software in behavior or performance that does not match our expectation. That is, by making our changes, our software has now regressed in behavior because it's now behaving in a way that we didn't want. So the demo that I've prepared for this is that same code that I showed you. So without further ado, I will just basically run it here. What you see I'm running is I have a student test. So I am basically saying Gradle Run Example, and I'm passing two arguments. The one argument is the version of my code. In this case, I would call this implementation version as version 1.0. And then I can pass now my test cases from the command line. In this case, I'm using Alice, Bob, and Charlie. And this way, by passing the Alice and Bob and Charlie, the test framework is going to pass each test case to this workflow and run this workflow every time. Every time, it may take some time for the test to run, for the workflow to run, but there is no kind of output. We could store these, kind of values that we are capturing in files, but we don't have to, because these test results are submitted to the kind of the third-party system, that kind of central location that hosts all of our test results. So in this case, I ran version 1. I can make further changes in my code and run another version. But the important thing here is now I basically can use and reuse my test workflow just to do regression testing without having to deal with files locally. Let's just say in my kind of code under test, I have this map that I am using to look up the profile information for people. So let me make changes here. I'm going to remove certain things, maybe the GPA of this course for Alice and say Bob, and that should do it. So I basically changed the full name of one of the students and the grade of 2 students. Now, because I made changes to my code under test, I am going to rename this version as 2. But now this is the second time I'm running the test, and therefore I don't even need to pass my test cases. Because there is that central location, the SDKs or the code that we have here, they could just basically retrieve the list of test cases from the server and would rerun the same test cases. So in this case, I ran all these kind of test cases through the code again, and as you see, the tests were basically passed. The reason they show as passed is because the test is basically saying, run. I even if there are differences, I don't want to say that these are regressions. Maybe the software engineer changed this intentionally. So therefore, we just say, we are going to give that feedback, the notification about the comparison results asynchronously to software engineers so that we don't break their build. In this case, as you see, if I click on my, kind of this suite that I just submitted to, now I have 2 test cases. Oh, I'm sorry, 2 versions submitted. And version 2 is now having some differences. It's also different in terms of runtime. The performance has changed too. This is because I have this kind of a sleep that takes some random number. But again, if I click on version 2, I see that now Alice and Bob test cases now have differences. So I can click on Alice and I see that GPA has changed because we changed the courses, the GPA has changed. The GPA was calculated somewhere else. It wasn't the code that I changed, but this way, as long as I'm tracking the GPA somewhere, then I can find the side effects of that change that I made to the grade point average. The grade of some course for Alice. And then you see that full name is different too. So the idea here is the software engineer could then go, submit their change, and then they get that kind of email or a Slack notification that, hey, there are differences compared to your baseline. So they could go inspect the results, and if these results are matching their expectations, in that case, then they could decide to promote this new version as the baseline version, the version that they trust. So they could just easily promote it. And from now on, every time that we submit new versions, the server would automatically compare the results against the results of version 2. So by automating this kind of comparison, then now we kind of complete the feedback cycle for software engineers. We don't do full automation. Again, there is that kind of manual step of making sense of the differences, which is required for us to work. But because the rest is all automatic, now this gives us the potential to do this workflow continuously. And by continuously, I mean for every code change now, instead of once every every day or every week, you could just basically say, as our CI pipeline is running our unit test, so maybe it could just basically run our Tuka test. In this case, the workflows that I showed you. And it doesn't have to be Tuka. Of course, I built this software. I left my job and I started a startup because I didn't find any kind of tool that fills this gap in the market. But I'm sure like this concept is kind of, you could write your own system if you want to. You don't have to kind of buy any software from us. So I find that I hope that like again, software engineers find kind of consolation in the new tools in the market that would enable kind of shorter feedback cycle for them and make their life easier in terms of writing tests that give high return on investment. One way that I felt we could help is by basically building the software that kind of you can submit different results and get feedback automatically. Not just for you, but also for your team, because we all, as we know, software is built by teams. So therefore, it's important that we all are on the same page about how our software is behaving. So it's, in my opinion, as the final kind of conclusion to my demo, I would say I think that the testing kind of a stage in the outer loop of the business organization, the iteration loop, is so important that it should be done by engineering teams. And if there are not enough tools in the market that kind of fill the needs of the engineering teams, then we need to build those tools and make sure that we could basically give the value to engineers that want the feedback cycle to go ahead and make changes, make improvements, maybe just clean up the litter in the code that they are reading from the, time to time. All right, with that, sorry I went over time, but here are the links to the repo, the Tuka case, the GitHub repo. I added the link to because I want to announce that we are open sourcing the entire Tuka source code, even the source code for that kind of server that I showed you, the web app that had visualization, all that, next week. We do this because it took us a year to understand that we are building a tool for developers, and developers, they want to, to be able to use a tool for free. They don't want to like rely on a kind of company to, exist and, live around as long as they are building software. So I hope that this is a step in the right direction. So keep an eye on this repo. We're going to add the, certain components that are right now missing next week, and we have an announcement that would be coming. And while you're at it, if you are in this repo, I'd really appreciate it if you give us a star to make other people find us too. So thank you once again, and thanks.